Good evening. Today I am going to explain the electric field intensity expressions due to point charge, due to charged conducting sphere, spherical shell and so on. So, first let us try to find out electric field intensity due to a point charge. Let us consider a point charge plus q at this and due to this point charge we want to find out electric field intensity at this point P. Let the distance of the point P from the charge be r. So, we want to find out electric field intensity at the point P due to the charge q here. From the definition, electric field intensity at any point is force experienced by a unit positive charge placed at that point. So, to find electric field intensity at the point P, you have to imagine a unit positive charge at that point. Unit positive charge means positive charge with magnitude 1. Now, here let us take this charge. Q1 is equal to Q and Q2 is equal to 1 here. From definition, force acting on this unit positive charge is nothing but electric field intensity at that point. From Coulomb's law, force on this due to this charge is, because of repulsion, it will be in this direction, and that is given by 1 by 4 pi epsilon naught q1 q2 by r square. Here in this particular case 1 by 4 pi epsilon naught q1 is q, q2 is 1 by r square. So, electric field intensity at a point at a distance r from a point charge q is 1 by 4 pi epsilon naught q by r square. Due to a positive charge at any point, electric field intensity is away, because you have to imagine a unit positive charge, repulsion will be in this direction. So, due to a positive charge, electric field is away. If this is a negative charge, electric field intensity will be towards. So, that is the first case, electric field intensity due to a point charge. Next, let us go to electric field intensity due to number of charges, number of point charges. See here, there are number of point charges q1, q2, q3 like this. P is a point at which we want to find out electric field intensity. Let us assume all the charges are positive. So, electric field intensity at the point P due to q1 will be in this direction. Due to q2, it will be in this direction. Due to q3, it will be in this direction. E1 bar, E2 bar, E3 bar. So, the resultant electric field intensity at the point P is the vector sum of all the individual fields, E1 bar plus E2 bar plus E3 bar. Is it okay? Just I will tell you one example based on this. See, example. Find electric field intensity at any charge placed at the point P. So, this is the diagram given. This is an equilateral triangle of side A. Okay, plus Q and plus Q. 3 charges are placed at 3 corners. You are asked to find out electric field intensity at any one of the corners. This is the point P where you need to find out electric field intensity. Find E at the point P. Now, due to this positive charge, electric field intensity is away. Due to this positive charge, electric field intensity is away. Let us take this as E1. Due to this, let us take this as E2. E1 is equal to 1 by 4 pi epsilon naught. I am drinking water. E1 is 1 by 4 pi epsilon naught Q1 by square of this distance. This is an equilateral triangle of side A. So, 1 by 4 pi epsilon naught Q1 by A square. E2 1 by 4 pi epsilon naught Q2. Q2 by this distance is A, that is Q2 by A square. Here both the charges are equal in magnitude. Q1 and Q2 are equal. So, electric field intensities at the point P due to the individual charges Q each are 1 by 4 pi epsilon naught Q by A square. So, I am telling you the same thing here. Look, this is plus Q, this is plus Q. At this point, due to this 1 by 4 pi epsilon naught Q by A square, due to this 1 by 4 pi epsilon naught Q by A square. Angle between them, as this is an equilateral triangle, angle between them is 60 degrees. So, here resultant of two vectors of same magnitude at an angle 60 is root 3 times the individual vector. So, root 3 times E1, so root 3 times 1 by 4 pi epsilon naught Q by A square. So, that means the result, this is E1 say, E2, and this is the resultant electric field intensity, which is the vector sum of those two individual intensities created by the 2 point charges. If we have number of charges, we have to find out electric field intensity due to all the individual charges at that point. Considering the directions, we have to find out the vector sum of all the individual electric field intensities at that point. So, that is electric field intensity at any point due to number of charges. And now, let us go to a conducting solid sphere. Conducting solid sphere or spherical shell, both mean the same in this context. So, spherical shell of charge Q and radius R. So, let us imagine this as a conducting sphere. Okay, it may be a solid, may be a hollow one. In both cases, we get the same results. That is why. So, this is a sphere given a charge Q. In case of a conducting sphere, charge resides on the surface of the sphere, because inside the conductor electric lines do not exist, hence electric field intensity inside that sphere is 0. Now, let us consider any point P outside the sphere at a distance r from the center. So, P is the outside point. At any outside point, P, r greater than r here, electric field intensity is. This entire charge behaves like a point charge concentrated at the center. So, due to that point charge concentrated at the center at this point, electric field intensity is simply 1 by 4 pi epsilon naught Q by R square. That is at any outside point. And the second case is on the surface. if the point is on the surface, this point is on the surface, R is equal to capital R, E is equal to 1 by 4 pi epsilon naught Q by capital R square. And at any inside point, I already gave you the hint. What is electric field intensity at any inside point of any charged conductor? It is 0 because electric lines do not exist inside any conductor. So, at any outside point, 1 by 4 pi epsilon naught Q by R square, where R is the distance of the point from the center. On the surface, Q by capital R square. At any inside point, it is 0. Now, let us draw a graph between the distance of the point from the center along x-axis and electric field intensity along y-axis. See here, E as a function of R, and this is a point where R is equal to R. So, this point represents the point lying on the surface. So, on the surface, electric field intensity is 1 by 4 pi epsilon naught Q by R square. At any outside point, E is inversely proportional to R square. So, the graph will be like this. This is the outside point. As E is inversely proportional to R square, it will be like this. Very interesting thing is, at any inside point, as the electric field is 0, it is like this. This is the center. So, inside point, electric field intensity is 0, and on the surface it is maximum, and from the surface away from the center, electric field intensity is inversely proportional to R square. This is the graph representing the variation of electric field intensity due to a charged conducting sphere. So, next we are going to see a charged non-conducting sphere. Charged non-conducting sphere. Non-conducting sphere of charge Q, radius R with uniform charge density. This is important. With uniform charge density. So, that is a non-conducting sphere, charge uniformly distributed over the entire volume of the sphere. Okay? So, this is a charged non-conducting sphere of total charge Q and radius R. Let us consider an outside point P, which is at a distance R from the center. So, electric field intensity at that point will be equal to 1 by 4 pi epsilon naught Q by R square when R is greater than capital R. It just behaves like a point charge concentrated at the center. Now, second point, at any point on the surface, of the sphere, R is equal to capital R. From this expression, E is equal to 1 by 4 pi epsilon naught Q by R square. Till then, absolutely there is no problem, right? And the third case, look here, at any inside point, So, let us consider a point P inside at a distance small r from it. So, at P, where R is less than capital R, electric field intensity is 1 by 4 pi epsilon naught Q dash by R square, where Q dash is the charge enclosed inside the sphere of radius R. Q dash is the charge enclosed by it inside, by this sphere inside. So, here we want to find out q dash. See here, the total charge q by 4 by 3 pi r cube is pi r cube, is the charge density, charge per unit volume of the sphere, charge divided by unit volume. Per unit volume, the charge enclosed is q by 4 by 3 pi r cube. Now we want to find out the charge enclosed in this volume, whose volume is 4 by 3 pi r cube. So the charge inside this sphere will be equal to q by 4 by 3 pi r cube into this. 4 by 3 pi, 4 by 3 pi gets cancelled. Q dash is equal to q by capital R cube into small r cube. Substitute that in the first expression. So electric field intensity at any inside point of a non-conducting sphere 1 by 4 pi epsilon naught, q dash is q r cube by capital R cube by r square. So this is implies at any inside point, electric field intensity E is equal to 1 by 4 pi epsilon naught q into r by r cube. Right? This implies at any inside point, electric field intensity is directly proportional to R, and at any outside point, E is inversely proportional to R square. Is it clear? It's very simple. If it is a spherical shell or conducting sphere, at any outside point 1 by 4 pi epsilon naught q by small r square, on the surface 1 by 4 pi epsilon naught q by capital R square. At both are same in solid conducting sphere or a non-conducting sphere. In all the cases, at any outside point on the surface E is same. But at any inside point of a spherical shell, E is equal to 0. At any inside point of a non-conducting sphere, E is equal to 1 by 4 pi epsilon naught q r by r cube. Now, if you draw a graph between the distance from the center along x axis and E along y axis, and this is a point on the surface. So, on the surface, electric field intensity is q by capital R square, and E is inversely proportional to R square. It will be like that. E is inversely proportional to R square. The graph is like this. Now, at any inside point, E is proportional to R. So, if E is proportional to R, it is a straight line passing through the origin. This is very important. In the previous case, inside point 0, but here it is directly proportional to R. So, the graph is a straight line passing through the origin. So, that is about electric field intensity due to a non-conducting sphere. So, here just we learn 4 points. Due to a point charge, electric field intensity is 1 by 4 pi epsilon naught q by r square. Due to number of charges, electric field intensity is the vector sum of the individual field strengths at that point. Due to a spherical shell or conducting sphere, 1. At any outside point, R greater than capital R, E is 1 by 4 pi epsilon naught q by r square, E inversely proportional to r square. Right? And at any point on the surface, at any point on the surface. On the surface, E is equal to 1 by 4 pi epsilon naught q by capital R square. At any inside point, E is equal to 0. Okay? So, outside point, on the surface, inside point. If you go to a non-conducting sphere, at any outside point, same, 1 by 4 pi epsilon naught q by R square. On the surface, same, 1 by 4 pi epsilon naught q by capital R square. At any inside point, it is 1 by 4 pi epsilon naught q small r by r cube. Okay, so these things we have discussed in today's class. Okay, so I'll stop here for today and I'll continue all the different cases in the next session. Thank you and bye-bye.